Good morning, everyone, once again. We are ready to start session number 3, which is BIM and Digital Prototypes 1. And I'd like to welcome to the stage Mr. Panayiotou. So big round of applause for our first presenter for this panel. Yes. Use this one.
Yes. All right. Thanks, everyone. All right, perfect. So, my name is Panayiotou. I'm a PhD student at the University of Cyprus, Department of Architecture. My supervisor is Odysseas Kontovourkis. And we did this, and this research is made under his supervision. Also, just to mention, Odysseas Kontovourkis is going to organize their EKD 2024, which is next year, just to mention that. This research is based on a Scan-to-BIM methodology for the digital reconstruction of timber structures. The aim and objectives, the development of a unified computational design framework that incorporates different types of timber roof structures, the ability for a much more detailed geometrical 3D model compared to previous research works where the geometry was created by extrusion, leading to simplified geometries. And third, the development for a data-rich building information modeling BIM attribute catalog for the reuse and maintenance of timber structures. The methodology starts with the typological organization of timber roof systems according to their geometrical characteristics. Then is the Scan-to-BIM workflow for the automatic creation of 3D geometry from point cloud data. And then is the specification of BIM attributes from existing timber structures. The typologies are related to heritage buildings, but also buildings to be reconstructed and demolished with a timber roof construction. The aim of the typological organization is to assist the Scan-to-BIM methodology by organizing early in advance the capturing of existing data, the segmentation, and the creation of BIM geometry with high levels of detail. Furthermore, the typology of the structures and the respective geometrical data contains material and structural attributes that allow the examination of the level of maintenance. This is the Scan-to-BIM workflow. It starts with a geometrical survey using terrestrial laser scanning through a tool, through Faro Focus Laser Scanner. And then this data is registered, the point cloud is registered within Faro Scene. After the point cloud is exported, it is cleaned using Agisoft Metashape, and then the point cloud is segmented using Cockroach plugin within Grasshopper. After the segmentation, there's an algorithmic process in Grasshopper plugin in Rhino and Largebox plugin, which starts with the detection of boundary points from surfaces, the creation of section curves from the boundary points, and lofted geometry from the curves, and the creation of a closed BREP 3D geometry. And this 3D geometry is basically synchronized with a BIM database using the Rhino Inside Revit plugin within Autodesk Revit and Grasshopper. The BIM attributes include the existing material, the volume, the cost per cubic meter, and cost emission calculations. Also, the attributes are processed, as I said, in Autodesk Revit using the Hawkins-Brown emission reduction tool with a material library that contains data from the Bath University Inventory of Carbon and Energy 2011. The existing timber structure is classified according to a predefined ID for each timber element. This is the case study that is made in Cyprus. This is St. Nicholas Church. It is a church built in the 16th century and is located in Galata, which is a village in Solea Valley, Cyprus. The building is a single nave chapel with a gable timber roof structure. The internal width is 3.6 meters and the length is 7.11 meters. As you can see on the image on the left is the church, and then on the right, you can see the existing timber roof construction. Number 1 indicates the rafter. Number 2 is the rafter tie. 3 is the ridge. 4 is the wall plate, and 5 is the batten. As I said, the terrestrial laser scanning survey is made inside the church in order to capture the point cloud data of the timber structure that is visible. Initially, the point cloud is downsampled to 25%, which leads to 16 million points to let the segmentation algorithm to work efficiently. And the first set of parameters provide 499 segments. And this table basically includes the parameters, the segmentation parameters that are used in Cockroach plugin for Grasshopper. As you can see on segmentation parameters number 1, which has 16 million points, the voxel size search and normal threshold degree are defined. The minimum cluster size, the color of point cloud to be true and split true as well, and that gives us the first set of segments, which are 499. And then these segments from this parameter are sub-segmented in order to create groups for each timber beam. So number 2 to 23 are the sub-segmentations, and specifically the rafter segments are identified through settings number 1 to 6, and the rafter ties from settings number 7 to 23. And each parameter has different points, and also there's a certain voxel size search and normal threshold degree that is set so that to achieve the better segmentation. This image shows on the left, you can see the point cloud data that is exported straight from the Faro laser scanner. And on the right, B is the initial segmentation result from parameter number 1. The rafter and rafter ties which are visible from the interior are further processed, and these provide us a total number of point segments, which are 739. Which need to be further classified in order to form groups for each timber beam. The segments representing the timber rafters are baked, allowing them to be easily set in Grasshopper, and the rafter ties are classified using the list item tool. The overall result of these groups of segments provides at least 3 phases of each beam, which are classified as bottom face, left face, and right face. Some beams that are attached to the wall can only provide 2 phases due to their limited visibility. In addition, some other beams were not fully scanned due to obstacles such as the iconostasis, which separates the sanctuary from the nave, and lighting fixtures from the ceiling. So this diagram, as you can see on the left, is the sub-segmentations which were further processed, as I mentioned before. And as you can see, the number 1 indicates the rafter, and number 2 the rafter ties, and these are repeated for each beam. So each timber beam is classified to a certain group. And on the right, it's the point cloud, a segmented point cloud from a rafter. Number 1 is the left face, 2 is the right face, and 3 is the bottom face. And I had to classify it into this way so that to let the algorithm to identify which one is left, right, and bottom face to tell to the algorithm. Yeah. This diagram on the left indicates the workflow that is made in Grasshopper for a certain timber rafter. It starts with a point cloud of a beam, and basically the points are exploded to XYZ coordinates. Then the boundary of each cloud is identified using convex hull tool, and the points along with the boundary are imported into patch surface tool for the creation of the beam faces. And then on the image, on the third image, you can see the boundary points and section curves. Basically, the bottom central axis is detected, and rectangular planes perpendicular to the other axis are formed. The planes are intersected with the geometry of the faces, and the boundary points are created along the edge of the faces. Irregular section curves of each beam are created which follow the geometry of the existing structure. And as you can see, on the faces, these are the points that are detected, which are necessary to identify the geometry of the existing beam. And the lines that you see are the connections of these points that create 100 to 300 section curves according to the type of geometry developed. And on the bottom is the closed BREP 3D geometry created. This is the deviation from the 3D geometry. For the rafters, it provides really good results because the deviation is between minus 7.7 millimeters to 9.2 millimeters. And this indicates a higher accuracy value than the rafter ties due to the efficiency of the algorithm to generate 3D geometry of timber beams with a rectangular cross-section. In contrast to this, the rafter ties had lower accuracy, and the deviation was between minus 88 to 92 millimeters. And this happens because their cross-section is octagonal rather than rectangular, and the generated geometry is simplified to a rectangular cross-section. The synchronization of these 3D data created is synchronized within Autodesk Revit using, as I said, the Rhino Inside Revit plugin. The geometry direct shape is used, and also the category is defined, which is structural framing, the 3D geometry, and the corresponding material. And the material that is used from the HBIRD library is HBA wood softwood, because the existing material is pine timber. And furthermore, an ID is also set for each beam. This is the geometry that is automatically generated and is synchronized within BIM software. On the left is the top perspective view, and on the right is the roof plan. And as you can clearly see, there's some irregularities detected due to the architecture of the building, which is a heritage building, and usually these buildings have irregularities. These are the BIM attributes from this process. On the left, you can see the ID that is defined for each beam, the material, and then the volume is detected, the total cost per square meter, and the overall embodied carbon sum. And in total, the beams are 47, but eventually 11 out of these beams the volume of 11 out of these beams could not be calculated due to scanning issues mentioned previously. In conclusion, preliminary results derived from Scan-to-BIM approach show great potential for its effective application in digital reconstruction due to the low deviation values achieved. The evaluation of average deviation values that range between minus 7.7 millimeters to 9.2 millimeters for the rafters indicate that the 3D geometry is highly accurate and close to the as-built geometry in case of beams with a rectangular cross-section. In the case of rafter ties with octagonal cross-sections, the average deviation values that range between minus 88 to 92 millimeters show that further investigation is necessary both in scanning and in 3D modeling stage. The automated transferring and synchronization of 3D geometry from the parametric environment to the BIM environment provides a platform for data development that can lead to further processing. The potential for calculating CO2 emissions along with the corresponding cost for each timber beam provide us with BIM attributes that allow decisions to be made as regards the preservation, recycling, and reuse of existing timber elements. Future studies may include additional laser scans in the interior of the church in order to capture the missing volume of the geometry from 11 beams that could not be calculated in BIM. And further laser scanning could be done on the exterior of the church for achieving the generation of 3D geometry of more timber structural elements such as the ridge, wall plate, and battens. Further research is also necessary for a much more detailed result for the rafter ties that contain octagonal cross-sections. And I think I'm done. This is, thank you for your attention.
Thank you. Thank you. Now we will start the discussion and questions. Yes.
Thanks for your presentation. Did you think about the interlocking joints between the beams elements? I mean, the joints between the elements. How you think? How does the different joints is going to affect these numbers you showed?
Yeah, as I said, this is an initial process. Only the rafter ties and the rafters are identified because are visible from the interior. So they could be processed. In order to also find the joints, I have to do a scanning on the outside because I can show you an image. I don't know if... So as you can see here, on the top is the ridge. So this ridge is visible from the outside, from the exterior. So I had to find the cross-section of that and then generate that geometry, and then it's going to be connected with the other ones. The same with the wall plate, because it's not visible from the inside. It's visible also from the outside, so the same happens there. So if I have this, then on beam, this could be connected.
Thank you. Next questions. Yes.
Hello. Thank you for the presentation. I missed the start a little bit, so I didn't know what you really focus on. Is the CO2 thing the main focus, or what do you want to achieve with it?
The main focus is basically mainly the creation of the automatic generation of 3D geometry from point cloud data.
Okay.
Which is
then I understand, because in this case I was wondering if it is necessary to have so much precision, because you could just imagine that, okay, these beams would be of similar size, and as long as you have the number of that, you can have a rough calculation pretty quick about, and many of them probably are the same size. And it doesn't really matter if on the fifth comma there is something different. So I think, but to show the workflow, it makes sense. Yeah, I understand that.
Yeah. Yeah, the aim is to identify also the irregularities of the geometries, because at Tilt, it's a heritage building.
Sure.
Yeah.
Yeah, because wood and old wood, yeah, is never the same. But it depends what you want to have as an outcome.
But the rafter ties have different dimensions, but not that much, as you said. But there's some changes on the volume and yeah. Yeah,
but okay, it's a question of how many numbers behind the 0 point, it really matters.
Yeah.
So, but therefore I was wondering, because, but it's an interesting workflow and it might be usable for a lot of things. Thanks.
Thank you.
Thank you for the presentation. It was super interesting. And now, after the workflow is created, I was interested in how much user workforce is required to put. Is it already scanning and then uploading the file and you can get the result? Or you have to intervene somewhere in the meantime? I mean, in already done workflow?
Let's go to the... So yeah, what's the question again? Sorry, because I just put the workflow. Yeah, let's see the workflow.
Where the user, like the final user, I know that to create the workflow, your ideas had to be translated, but now the final user, where does he interfere with this workflow?
Okay, so you mean if there are many users through that workflow?
No, you have the scanned point cloud.
Yeah.
You upload it to the script.
Yeah.
And do you have to make some interscript actions, or you just get an answer in form of BIM file?
Yeah. Okay. The points are within Grasshopper. As I said, they are exported into coordinates. So these coordinates are on each point of the beam. So the coordinates define where the beam is placed. And then according to these coordinates, as you can see on this image, each face is created separately. The boundary of each face is detected, and this gives us the edge for each beam, and sections are created basically on the beam, and this provides us with the points on the edge. So using this workflow, you can have the whole beam and also the irregularities, because each section is different, because it's tilted. The beam is a bit, I don't think, maybe it's visible from the geometry as well. So that's how it works basically, and the lofted geometry is created.
So it happens automatically from point cloud to closed geometry.
Yes. You put that. Yeah, it happens automatically. Yes, as long as the algorithm is done correctly. Yeah, there's always changes that need to be made. Obviously, there's some, because the point cloud is too heavy data. So, but yeah, it worked. I tried it for every beam and it worked.
So when you have the point cloud data, then you have to manually somehow adjust it and let's say make it not so heavy so the algorithm can work it properly. Exactly,
yeah. What has been done, as I said, the point cloud was downsampled.
Yeah.
So the initial points were around 64 million. So only the 25% of these points are used, because then it would be too heavy and the algorithm wouldn't work.
And when you showed us the different sides of the certain beam, you need to define those sides manually for it to work, or the algorithm somehow can detect that this is a beam and it has 3 or 4 sides?
Yeah, that's a good question. Yeah. Right now, it's, as I said, on left face, bottom face, and right face are defined manually. They are like set, the cloud is set manually. But obviously, it's a good next step, let's say, to use maybe machine learning or these processes to detect the phases automatically.
Okay, thank you.
Hello, thank you for the presentation. And I would maybe ask, like, in this process, you were talking about this specific case study about the church. Yeah. So if you think like to apply the same method on different place, do you think it is like general way that would work for any other similar structure, or is there something specific for this church that you considered?
Yeah, good question. The aim is to apply this to different types of architecture as well, to different types of timber roofs. Yeah, that's the whole point, to apply it, to try it into different types of architecture, not only this, but other churches as well.
Yeah, thank you for the presentation. I think you just answered my question. But to extend that was also, so your intention is also to create this for different forms, right? Or because now you have the 3 phases. Are you intending to try to create a similar script for other forms?
Yeah, the timber rafters have an octagonal cross-section. And a challenge is to also manage to identify different types of cross-sections, not only rectangular. Yeah, it needs more developing to do that.
Okay, thank you very much for your presentation. I'd like to ask you about these cultural heritage issues, because we can say, okay, there is a lot of numbers after comma on one hand, and on the other hand, what is the approach in Cyprus to cultural heritage buildings and replacement of elements? What is the old school, new school? How do you proceed? Are you very aware of detailed sizes of original elements, or because it is kind of a purpose of this work, I guess. Yes, you have the structure, and maybe it needs maintenance, and then your work is well, perfectly useful for that. But do you know what is behind it? What is the?
Yeah, definitely. There's many buildings in Cyprus that need to be refurbished, especially their timber structure, which timber is a very sensitive material. And through a process that is more automated, you can analyze the existing material in a better way, because heritage buildings have all these irregularities and sensitivities. Also, through laser scanning, you don't need to disassemble the building completely. Like, you don't, because there's rules for heritage buildings that you don't need to touch this, touch that. So through using just your scanner and getting the data, you go back to the drawing board and you analyze it, and you sort of make decisions either to replace a certain timber beam, maintain it.
Right.
Yeah.
So let's go with this replacement option. If you have to replace it, what would be the new element? Is it like resembling in totally detail what was there?
Yeah, it should be.
Or
the new element definitely should be the same material. If it's pine timber, specifically that timber is from the surrounding area, so maybe it's better to use the same material from the surrounding area. Yeah.
Yes,
same
but what
size.
about sizes? I mean,
the size as well. If it's important to use the same size, then.
Yeah, but maybe I'm not putting my question right. Let's go for an example. Examples from Poland. So this like old and new school, and a lot of schools towards this topic. But generally, the people who are in care of old buildings, they would not like new elements, like brand new from CNC machines, to be put there. On the other hand, we may discuss that, okay, this structure is kind of regular, but you discovered that each rafter is a little bit different, yes? And does it matter or not? Was it just because it was handmade, yes? So kind of a human, let's say, capacity to make them as the same as possible at that time, or maybe it was like a climate, moisture, etc., that changed these beams, these elements, slightly over the years or decades or centuries. So if we have such case in Poland, that is a huge always discussion, what to do, what to replace, and how to replace it. So so if these, as I said, these values after comma matter or not, yes, to make the element that you are replacing totally the same or similar.
Yeah. For example, this rafter tie, it was a sort of sculpture, as you can see on the center. It is sculptured with Byzantine methods, sculpturing wood. So let's say that beam is destroyed for certain reason and it needs to be replaced. The best way, I believe, is to find someone who can remake it, either by hand, obviously, but if that's not possible, then you can scan it in much more detail and then process it so that you know the geometry and recreate it.
Okay, thank you. Thank you very much.
Okay, any further questions we'll have to make during the coffee break and the lunch, as we are kind of behind schedule. So once again, thank you for your presentation.
Thank you.
And thank you for the amazing discussion.